So first, thank you, Stella, for inviting me and giving me this opportunity to talk to you. And thank you, everyone, for attending this talk this afternoon. So sorry for not being able to be here, but with the current situation, I guess it's best to do this online. And hopefully, if you have some questions or want to discuss more on this or something else, I will be at École Polytechnique quite often, as Stella mentioned. So in this talk, I would like to speak about some generalized continuum model, which we call a multiphase continuum, which, as you will see, will extend the classical Cauchy continuum, and which will give us the opportunity to model interesting features, especially in fiber reinforced materials. So we'll speak about a first part will be on the homogenization of such materials from heterogeneous microstructure, and then I will speak about some modeling of fracture and debonding in fiber reinforced materials with such a model. So what I'm interested in here is fracture processes in fiber reinforced materials. So here it will be mostly on long fibers. So as you may know, it's quite complex because you have anisotropy, you have heterogeneous material due to the fibers and the matrix. You also have interface properties between the matrix and the fibers. And so you can have a multitude of different failure mechanisms, because if you apply tensile loading in the transverse direction, you can have either matrix cracks or cracks that go inside the matrix and go along the interface between fibers and matrix. And also, if you load in the direction of the fibers, you can have fiber fracturing in the matrix, but fibers which may remain intact, and also debonding along the fiber interface. And this is the two phenomena that I will be interested in this talk. So interface debonding and the bridging effect of fibers in such a situation. So more complex aspects like fiber failure and plastification or friction during pullout of the fiber, I will not investigate here. And it's quite interesting for us at Laboratoire Navier, because even if we are a civil engineering lab, we have some applications with ultra high performance fiber reinforced concrete, as you can see on the left, and also some reinforcement systems, for instance, in old masonry structures, so mostly in Italy, where you have systems which are comprised of a grid of steel and some mortar on top, which is applied to all the masonry structure which may have been damaged. And when you study the strength properties of such reinforcement system, you can see multi-cracking in the matrix phase because the fibers still remain intact inside, and this is the kind of thing that we would want to address here. So, as I mentioned, I'm interested in the crack bridging mechanism. So you have intact fibers that still apply some forces on the crack, which is present only in the matrix phase, and a competition of the fact that the crack will continue propagating in the matrix is the fact that you can also debond the interface between the fiber and the matrix. And the competition between these two mechanisms is quite important, because it gives a toughening mechanism, which is quite interesting in biocomposites, for instance. And as you will see, this will give some pseudo-ductile behavior due to the presence of multi-cracking and debonding. So the question here is, how can we model this feature at the macroscopic scale? Because obviously we do not want to model explicitly all the fibers and the interfaces. So one possibility is to use cohesive zone models, where you have some ad hoc traction separation law when modeling the crack. But this requires some fitting or specific identification. And the question here in this talk is, can we reproduce this kind of crack bridging mechanism using only a continuum theory and that we could derive from homogenization, for instance? So the main issue here is that standard or classical homogenization has some issues, especially when you have a poor scale separation between the macroscopic scale of the structure and the scale of the heterogeneities, because you need to have a proper scale separation to apply standard techniques. And it doesn't treat well boundary layer effects that you can have, especially near free edges or around cracks, which is exactly what will happen here. And in some instances, it's also difficult to derive a proper homogenized behavior when you have multiple small parameters like the scale separation parameter, but also the slenderness of the heterogeneities or the contrast of properties between heterogeneities. And in fact, all these three situations can be quite frequent in fiber reinforced media. And the idea here is to use generalized continuum models that may provide some answers to these limitations. So as I said, in fact, the standard Cauchy continuum cannot model the bridging region in an appropriate manner because, as you may have seen, in the matrix phase, you have a crack-free surface, you have opening displacement on the matrix phase, whereas the fiber, they remain fixed. And if you look at the symmetry plane, their displacement is fixed. So you cannot model in a single continuum which mixes both phases, the fact that you have a crack-free surface in the matrix and a fixed displacement in the fiber. And also, as everyone knows, the Cauchy continuum doesn't have any scale effect, so you cannot reproduce the fact that the cracking processes will strongly depend on the fiber size and give a size effect in such materials. So here we'll propose a generalized framework to account for all these aspects and investigate how we can model fracturing and debonding in such materials. So here I will present the multiphase continuum model. So the idea is that you replace the heterogeneous material by, in fact, two homogeneous phases. Let's say a matrix phase and a reinforcement phase. And both of these phases will have different kinematics, so namely two different displacement vectors, which I call UM and UR. And of importance is the relative displacement between the two phases. And you have many ways to formulate such theory. You can build them from the virtual work principle by just assuming that you will have a first gradient theory that the work of deformation will involve the strain of both displacements and also the relative displacement of between the two phases. And when you assume this kind of expression for the deformation work density, you can identify with respect to each strain measures here some generalized stress measures that will be associated. So in terms of strains, we have the strain of the matrix displacement and the reinforcement displacement, the relative displacement between the two phases. And associated with that, we will have a partial matrix stress, a partial reinforcement stress, and some additional stress, which we'll call an interaction force, which is a vector and which is related to the relative displacement. And when we impose the fact that both phases have the same displacement, the same kinematics, then we recover the standard Cauchy medium because we have only one strain measure, the relative displacement being 0. And in this case, we have the Cauchy stress, which will be the sum of the two partial stresses. So for people who know porous mechanics, this is exactly the same framework of having a matrix skeleton and a porous phase, except that in porous medium we have a solid and a fluid, but here basically we have two solids which share the same material point at the macroscopic point at the macroscopic level. So if we use the virtual work principle, we can derive the balance equations at the macroscopic scale. So you'll see that the divergence of the partial stresses are related to this interaction force and to some body force that can act on both faces. And again, if you sum these two equations, you recover the standard Cauchy continuum balance equation. So the main question here is, what is the micromechanical interpretation of these quantities? So if we define, so we assume that we have a unit cell A of heterogeneous material and an interface gamma between the two faces, matrix and reinforcement. And if we define the resultant force I, the average resultant force over the interface as being the interaction force I, then we can show from partial stress balance at the microscopic scale, we can derive the partial stress balance at the macroscopic scale exactly like this, so following Poussy, for instance, where the partial stress, so you can see it's exactly the same force as above, the partial stress is defined as the average of the stress over each phases. Okay, so which I will denote like that. So you have the volume fraction and the average over the phases AI. And so this gives us the main elements to derive an auxiliary problem, to go from the standard microscopic problem to derive the apparent properties of this generalized continuum model. Because the main issues when we work with generalized continua is how to compute the modulus, elastic modulus, and so on, generalized modulus that will appear when we assume an elastic behavior, for instance. So here I will do it in the elastic setting. So here I consider a generalized auxiliary problem compared to what we usually do in standard homogenization. So the main difference here, we are in the periodic in a periodic setting where I apply some macroscopic strain on the boundary of the domain, and U will be a periodic fluctuation of the displacement field inside the domain. And the main difference is that I will additionally consider two eigenstrains, in both phases, and two uniform body forces in two stresses. So F here. So that's quite different from standard homogenization. But in addition, I will assume that these eigenstrains and body forces are, as I said, phase-wise uniform and are of 0 average over the two phases. So if F, for instance, is of 0 average, then I can just replace it with a vector that I will call I, and I divide by the two volume fractions of the faces, so that if I take the average of such F, it will be of 0 average. And I can do the same for the eigenstrains by introducing some tensor that I call delta E. And if we do that, in fact, we can, instead of piloting the problem with the macroscopic strain, and this delta E, we can equivalently work with some EI, which will be redefined like that, with the relation between the EIs and the macroscopic E and delta E like that. And when we do that, in fact, we have a problem, an auxiliary problem with 3 different and independent loading parameters, so E1, E2, and I. And so I can solve this problem in an elastic setting. And I can show, using an extended version of Hill-Mandel's lemma, that the dual quantities to these three loading parameters are exactly given by the microscopic interpretation that I gave earlier of sigma I being the partial stress with the average stress on the phase I, and the quantity which is associated with the interaction force. It's something that is homogeneous to a displacement. I call it V, is the relative average, the difference of the average displacement in both phases. So U2 minus U1. So it's exactly what we would expect from the ideas that drive the construction of this model. And when we have these three loading parameters in elasticity, then we can write that the solution to the auxiliary problem depends linearly upon the three quantities. So we introduce some localization tensors, and we can compute then the partial stresses and the macroscopic relative displacement V. And this will give us some apparent moduli, D11, D12, D22, etc. And these in bold here are in fact third order tensors because they relate a second order tensor and a vector. Using the Maxwell-Betti reciprocity theorem, we can show that we have a symmetric behavior for this generalized behavior. And again, if we sum the two equations for the two partial stresses, and assuming that we have the same strain in both phases and zero interaction force, then we can recover the standard Cauchy apparent modulus C ohm, which will be related to the moduli D11. So C ohm, in fact, is D11 plus D12 plus D12 transpose plus D22. And in the case where we have a central symmetry, in fact, the third order tensor, they vanish. So we have a much simpler relation in the end, which is given here. So in fact, we can go one step further when we have only two faces, two homogeneous faces. We can deduce the partial interaction tensors Dij from the standard macroscopic stiffness CM with these relations. And so this give us directly the value of this macroscopic tensors. And then we can investigate some quite important case in practice. It's the case when the inclusions are isotropic, very stiff compared to the matrix, and in small volume fraction, which is quite often the case. So with this kind of assumptions and using results from Ashin and Rosen for cylindrical inclusion, we can show that the macroscopic stiffness, so that's standard homogenization results, is in fact given by the stiffness of the matrix phase plus some uniaxial stiffness in the direction number one of the fibers, with a modulus E naught, which is the limit of the fraction of the fiber times the modulus of the material which constitute the fibers. Okay, so that's why we assume that this limit is not zero in small volume fraction, because otherwise we don't see the effect of the fibers. And in this case, in fact, the above expression, they simplify quite nicely because we don't have any coupling anymore between the two strains. And we have only the modulus of the matrix phase is, as expected, the stiffness of the matrix material. And the modulus of the reinforcement phase is, in fact, only a uniaxial modulus in the direction of the fibers. So the fibers basically they behave like an elastic bar aligned in the direction one. And this gives us in the end the stress strain relations between the two faces. So we have a classical matrix, the classical behavior for the matrix phase, and only a uniaxial behavior in the fiber phase. But this is only valid in this case. So in this case, in the end, we can write the free energy density of this macroscopic continuum. So we have, again, three strains, a second order tensor, a scalar strain for the matrix, because we have only the elongation in the direction of the fibers, and the relative displacement between the two fibers. And we have this decomposition of the free energy density with the contribution from the matrix, the contribution from the fibers, and some additional term which is related to the interaction between the two faces. And this is what will be interesting here. This interface stiffness kappa is in fact given by the solution of the auxiliary problem that I presented before, when we have these self-equilibrated body forces, so with no eigenstrains. And in fact, this problem is quite similar to the homogenization of permeability in porous media. And you can see quite easily that this modulus kappa will depend on the unit cell size S. So you will have a scale effect in this interface stiffness kappa. So a simple example, when you have a 2D layered medium with eta as the volume fraction of the reinforcement. So the problem to compute kappa is very simple. You assume a uniform horizontal body force in the reinforcement, a uniform body force in the opposite direction with proper scaling, so that you have a zero average of the body force in total, and you compute the displacement of this problem in this case. So this is the typical shape of the displacement for the solution of this simple problem. And the computation show that kappa is related to the average of the inverse shear modulus, and divided by the square of the unit cell size. And in the case where you have a very stiff reinforcement in small volume fraction, this degenerate to this factor 12 times the shear modulus of the matrix phase divided by S squared. So this is what will be interesting, because when S goes to 0, so basically you have an infinite number of fibers, so you are really in the regime of complete scale separation between the microscopic and macroscopic scale. Then you can see that this interface stiffness kappa goes to infinity, which will penalize the displacement of both phases to be the same. And then we will recover the Cauchy continuum in this limit. So we can see these multiphase models as some extension of the Cauchy continuum when you don't have a perfect scale separation. And we'll see the implication on that on some solutions of elastic models. So in small strain situation with elastic behavior, we can just look at what would look like 1D solutions for such models. So when you do that, you have two coupled second order differential equations when you write the full equations of the problem. So you can see that you have coupling between the two displacement with the modulus here and with the interface stiffness kappa. And when you simplify with the case of small volume fraction, where you don't have this coupling with the elastic modulus, you have some equations that look like that, which are exactly the equations that you would get from the so-called shear lag models that are quite used to analyze stress transfers in composite, but which are often derived with assumptions that are not always clear and so on. So in fact, this multiphase model can be seen as a proper 3D generalization of shear line models with strong micromechanical grounds, let's say. Okay, and when you solve these equations, in fact, you can rearrange them by introducing a displacement W, which will be a common displacement of both phases, and plus or minus a relative displacement of the two faces that I denote J here. And when you do that, you can recombine the equations and you have these two uncoupled equations. And the first one is exactly the one you would get from the Cauchy continuum. So W would be the Cauchy displacement, and you can see the Cauchy stiffness that would arise in this setting. And you have another equation, which is Helmholtz type equations, because here it's only W with second derivative. Here you have J derived twice and J here. And so it means that you have a length scale that appears here that I denote L underscore B, which is given by that. So you have a length scale which appears from the moduli of each faces and which also involve the interaction stiffness that I discussed before. And as I said, this interaction stiffness scales with 1 over S squared. So it means that this length scale scales with S, and typically is of the order of S. So S, I recall, is the spacing between fibers. So if you normalize it with the typical length of a macroscopic structure, is the scale separation parameter. So basically what we will see is that this relative displacement J will be a boundary layer, basically. Okay, so here you have what happens in the bulk of the material, and you have some boundary layer equation that is given by J, and with a typical length scale, which is here given by the material parameters. So that's an example of what we can do. So in this setting, we can prescribe the displacement of both faces to be 0 on the left. And on the right, that's what's interesting, is that we can prescribe different types of boundary conditions for each phases, something which is not possible for the Cauchy continuum. So we can prescribe, for instance, that the matrix phase is stress-free on the right, and that the displacement of the fiber is given by some quantity U. So basically here we are doing some pull-out tests of the matrix fiber composite, so by just applying a displacement only on the fiber. And when you solve the equations, that's the expression that you get, and you can see that they involve this material length scale. And when you look at so here it's the different stresses. So the total stress is the sum of the two partial stress, the matrix in orange and the fiber in red. And so you can see that when you are far from the region where you have these mixed boundary conditions, you can show that you recover the Cauchy regime, let's say, where everything is almost uniform, and you have these boundary layer corrections near the boundary with the typical length that scales with this material parameter. Okay. So now we can do the same for a more complex 2D case. So here on the left, I assume that I have a rectangular domain of fibers and matrix, and I will add some matrix crack in the middle here. So the matrix phase will be stress-free on this domain, and the fiber will remain fixed because of symmetry conditions. So on the left, that's the heterogeneous problem. I will vary the spacing between the fibers. So I will consider different numbers of fibers across the height of the sample. And on the right, that's the homogenized problem with the multiphase continuum. So you will have a homogeneous material, except that in addition to the standard Cauchy continuum, where you will have only one displacement field, you have two displacement fields, and you can impose different boundary conditions on these two fields. So on the right, both fields have the same applied displacement delta horizontally. And on the matrix crack here, I will only prescribe the displacement of the fiber, which will remain fixed, and the matrix will have to fulfill a stress-free boundary condition. And then we can look, so on the left, we can look at the matrix displacement opening. So in solid lines, so across the height of the stiffness, the crack is here. So the solid lines are the results given by the multiphase model with a finite element implementation of this model. And the symbols are the average of the matrix displacement when I average it over some region of the matrix phase around the crack. So you can see that it's exactly what you would get, and that you recover the scale effect, because the more fibers you put, the less the matrix will be able to open. And in the limit where n goes to infinity, which would be what you would get from the Cauchy continuum, well, you cannot have any matrix displacement at this point, because you cannot fulfill the stress-free boundary condition and the fixed displacement boundary condition on this region. So that's why you have a boundary layer effect. And you can look at the same, you can validate that also on the shear stress at the interface, because the interface force I is related to the shear stress that happens at the interface. So from this quantity, you can recover the value of the interfacial shear stress, which is 0 when you are far from the matrix crack along the interface. But as you approach, you have a strong concentration of shear stress near the crack. And again, you can reproduce this scale effect, this dependency on the number of fibers. And you can also model a delaminated interface, because you can just assume that you have no interaction stiffness in some region here, with imposing this stiffness parameter kappa to 0. And then this will model the situation where you have interface that has delaminated between the fibers and the interface and the matrix. So this is again what has been validated. So the matrix displacement along the vertical direction here, and horizontal stress in the matrix and in the reinforcement along an horizontal line here, with 0 matrix stress inside the delaminated region, because you cannot have stress transfer between the matrix, which has a free boundary condition, and a free interface. So in this region, the matrix can carry no load, and then you have stress transfer between the fiber and the matrix, which can happen progressively on some length, which is related to this material length scale of the model. So now I will show how we can use such models to model matrix cracking and the propagation of interface debonding, because here in what I just presented, it was only elastic computations with fixed boundary conditions and fixed values of kappa in this region. So now we will formulate a coupled problem of matrix cracking and interface debonding. So the idea here is to use the formulation of Francfort and Margot from the variational formulation of fracture, but extended to this case. So here we assume that we have elastic fibers, but a brittle matrix phase and a brittle interface. Okay. So in the matrix phase, I will denote by gamma the cracks only on the matrix phase, and by delta the debonded region between the two phases. So we can formulate a total energy that consists of the elastic energy of the multiphase continuum with the stiffness of the strain stiffness of both faces and the interaction stiffness, the interface, the stiffness of the interface here. And in addition, the two fracture energies. So one for the matrix, which is GC of the matrix times the length of the crack gamma, plus the interface, the interfacial debonding energy of the interface delta on the debonded region. So this kind of formulation, in fact, is quite similar to some previous works that have been done. For instance, when you consider an elastic membrane that is connected by an elastic interface to some rigid support. So you can model cracking of the membrane and debonding of the interface. So that's quite a similar setting, except here is that the second phase will also be elastic and with the quantities here that have been derived from the homogenization procedure. So in the, I will introduce some parameter alpha, which you can interpret as a damage parameter of the interface, which will help to represent the debonded region. So the debonded region will be the points where alpha will be non-zero. And so in the case of stiff fibers and in small volume fraction, we have a simplified form of the energy because we just have the elastic energy of the matrix phase and this the additional elastic energy of the interface in the direction and the interface energy here. So the problem here is that we have some cracks in the matrix phase, and to be able to simulate fracture processes in the matrix phase, we will need to have some kind of regularization. And so again, here we follow the important works of Bourdin, Francfort, Marigot, and so on, and all the works related to damage gradient models or phase field approaches to fracture. So I will not go too much into the details. Some of you may know this kind of approaches. So here what we do is that we will have two damage parameters, let's say D and alpha. D will be the damage parameter related to the cracks in the matrix phase, and alpha, as I said, will be the damage parameter related to the debonding of the interface. And we will assume irreversible evolution of D and alpha. So to do that, we introduce a damage elastic energy of the matrix phase. So we just degrade the stiffness of the matrix phase by 1 minus D squared. We don't impact the stiffness of the fibers, so that's very important. It means that we are not in a setting where we have a full crack. When the matrix will have cracked, we still have some remaining stiffness due to the bonding effect of the fibers. And we also degrade the interface kappa, the interface stiffness kappa with 1 minus alpha squared, and we can change that if we want. And as regard the regularization of the matrix and the interface dissipated energy, So for the matrix, as I said, we have to regularize it, otherwise we have an ill-posed problem. And so we will add, in addition to a fixed, a local fracture energy, we have a regularizing gradient term with some additional length scale L0, which is the typical phase field regularization length, which some of you may know, which will have a different meaning compared to the material length scale that I denoted by LB before, which is purely a material length scale, which is given by the competition between the stiffness of the faces and the relative stiffness of the interface. So that's quite a classical assumption here, and we'll have also some density for the interface dissipated energy, W of alpha, and for that we can consider different models. I will show them later. So I will skip on the resolution. So it's quite standard. We have a variational inequality both for D and both for alpha. For alpha, we will have a local problem to solve, so it can be done in closed form expression for simple models. And for the D parameter, we have a global variational inequality problem to solve due to the presence of the gradient of D. So that's quite standard. And as regard numerical resolution, we use a Phoenix implementation, and we do a three-field alternate minimization to compute local optima. So we compute the displacement problem and then optimize over D and optimize over alpha and do some iterative process to converge to a locally optimal solution for all the fields. So that's just the two different debonding energy model that we can take. One which is linear with respect to the variable alpha, and one which is quadratic. So you have different response of the interaction force with respect to the separation of both faces. So one with an elastic phase and one with a much smoother evolution. So we can look at the difference. And so that's first application why you have a one-dimensional bar which has an initial matrix crack in the center, and you apply tensile loading. And here we are in the case where we have quite a strong interface. So given by the ratio of the two fracture energy of the interface and the matrix. And in this case, since the interface is 200 times tougher than the matrix, in fact, the interface cannot damage at this strain level, and you can only observe multiple matrix cracking. So you have multiple cracking because you still have some load carrying capacity due to the fibers, and you don't have only a single crack that would separate the bar into different pieces. Here you still have some load carrying capacity, so you will have different cracks on the regions. Here it's an example where we have a much weaker interface. So we have still the single crack that is inserted at the beginning of the computation. And when you load it, you don't have any more matrix cracking, but you just have the interface that damages. And so you have a debonding front that initiates near the matrix crack and propagates along the sample. And if you have some intermediate value for the ratios, you can have a competition between the propagation of debonding and the occurrence of matrix cracks. So that's the load deformation behaviors that you would get for these three different settings. And you can see that you have some pseudo-ductile response. So in blue, it's the apparent response of the composite. So you have initially an elastic phase, and you can have either elastic loading, matrix cracking, and a succession of matrix cracking events in the case where the interface is strong, or you have a phase of interface debonding propagation. But in both cases, you have this regime where the load is almost constant until you cannot damage anymore. And at the end, it's only the fibers that take all the rest of the loading capacity up to the final failure of the fiber that we don't model here. So this quasi-ductile behavior, although we have only brittle materials, is quite important. So just quickly, here it's also an experimental result of the crack spacing that you will observe in laminates with different fiber orientation. When you load in tension, you have the 90-degree ply here that will have multiple cracking across the ply thickness. And the crack spacing will depend on the thickness of the ply. So you really have an influence of the thickness of the ply on the spacing between the two, on the spacing between the multiple cracks. And this is something that we can have in these three simulations here. We vary the material parameters so that we have a different material length scale LB, which pilots the boundary layer. And you can see that this will change the number and the spacing of the cracks. So here we just have some issue at some point where when the material length scale becomes comparable with the regularization length scale of the phase field approach, then in this case we have some kind of diffuse damage, but which is only a numerical artifact, because if we take a much smaller regularization length with still the same value for the material length scale, then we recover multiple crackings with much closer spacing. Okay, and just to finish, this is an example where we have a bending of a beam, again with a pre-crack. So you have the crack which propagates along the height, and at the same time, the interface that debonds, because here we are in the case where the interface is quite weak, and again you have this pseudo-ductile response. And for the same setting, if you have a much stronger interface, then as you have seen, you will have multiple cracking of the beam along the span, and only very little interface damage. So this is typically the behavior of ultra high performance reinforced concrete, where the fibers, they are sufficiently strong to bridge the crack that will occur in the concrete phase, and this will give you a much higher strength and quasi-ductility even in tension for concrete material. So I think I will finish here. I will skip the extensions. We can discuss that if you want. So to conclude, these multiphase models, in fact, they can be seen as generalized continua, which are well suited to fiber reinforced material, and in fact, which can be obtained at the leading order from classical asymptotic expansion, meaning that if you have an extremely strong matrix material, then the boundary layer basically will cover the full length of your sample. In fact, it's not so often the case, and we can just see them as a correction of classical Cauchy continuum to account for what happens near the boundaries of such fiber reinforced material. And this is very important for accounting for all these matrix cracking processes, because this basically creates some new stress-free boundaries, and the boundary layer effects happens in the interesting region where damage takes place. So what's quite useful is that we can have a proper homogenization procedure to identify the generalized constitutive parameters, because that's often something which is lacking when you have other generalized continua like second gradient or micromorphic approaches, where the new constitutive parameters, you cannot quite easily compute them from microscopic properties. And we have also a very good mechanical interpretation of the generalized stresses. And this is quite useful to apply boundary conditions, for instance, because that's also a main issue in generalized continua when you have some generalized stresses that are associated to a second gradient of the displacement. You cannot really know what they mean, and it's quite often hard to come up with the proper boundary conditions. And as we have seen, we can include phase field or damage gradient approaches to account for fracture modeling in such generalized continua, because they are quite close to a Cauchy medium, because basically to Cauchy media in interaction with each other. So the open questions that remain is to have a proper comparison with full heterogeneous computations when we do matrix propagation and interface propagation, and maybe some more advanced model where we can couple a little bit more the effect of the interface debonding and the stiffness and some anisotropy. An important question is that when we have three fields to compute, the alternate minimization is quite hard to make converge when we have a simultaneous evolution of both variables, and then the computational cost is quite huge. And I guess that's it. So I will thank you for your attention.
Thank you very much,